Hey, from the review, are there any questions that you would like me to go over, Dorothy, my child? Number 15, you asked? I don't even know what number 15 is.
15B.
Okay, this is, I like part of number 15. I like part of number 15. I like part of number 15 on one of my tests. There's your hint. Okay. Let me see if I can copy and paste this. So we're going to go clip. Yoink. And then we're going to go a little further down. So you got the work done, okay?
Yeah.
How much work? It's going to be the area.
Mm-hmm.
All right. And what'd you get for that answer for A? Do you remember?
It was 0.94 joules.
And that was correct with the back as well?
Yeah.
Good. B says, assuming no losses due to heat, what's the maximum speed? What did you just figure out in part A? What do they ask you to find in part A? So as a good test writer, I'm kind of thinking, hey, maybe I'll use part A to get to B. I don't know, maybe. They're talking about heat and maximum speed. You know what? I think what they're saying is this. Work is also the change in potential plus the change in kinetic. Oh, plus anything goes to heat. Oh, then they said no heat. And also, because they said maximum speed, I think what we can assume is that we didn't lose anything to potential energy. Otherwise, they wouldn't have said the maximum speed. The maximum speed, I think what they're saying here, Dorothy, is all of that energy that you put into compressing the spring, all of the energy that I put into my Nerf dart gun in compressing that spring is going to turn into kinetic, in theory. So, maximum speed, I think we're going to assume we start from rest. So really what we're going to have is 0.94 joules work equals a half. Did they give me the mass of the car? Ah, they did at the very, very top. 0.03 V final squared. So it's going to be 0.94 divided by 0.5 divided by 0.03 square root, and that should get you that. Okay? How'd you find part C? Yeah, the efficiency is going to be, you know what? They're talking about joules. Hey, in part A, I got an answer in joules. How much how much work did I put in? 0.94 joules. How much am I getting out? 0.18. What's the efficiency? Gabrielle, you are correct. Smaller number. I don't use that very often, do I? Gabriella? It's okay. It won't be the first. It won't be the last time. Times 100%. Whatever the heck that is. Not very efficient. Neither is this. We actually crunched the numbers once. We pulled back with a spring, with a scale, to see how much force I had to put. We measured the distance. And I think theoretically they should come out of here at a fairly blistering pace, and then we actually timed it with the radar gun to see how fast it was coming out, and not very fast. My Nerf dart gun, well, you can hear it, and let's assume that's not greased very well in there at all. There's lots of energy going to heat and other dissipative forces. Is that okay, Dorothy? Yeah. Next. Oh, and again, same deal as any other tutorial. If you want to write this down, you can. If not, if you want to just watch, I'll print this up for you when you're done as well. Whoever wants copies. Yeah.
16.
Oh, since we're here, sure.
I know it's area under graph.
Yeah.
But why is it a specific way you draw the square or the rectangles? Because when I drew it, like...
I don't know. Let me copy it first, and then let me look at my answer key and see what I did. So it wants moving at 12 meters. So here's 0. Here's 12. So this is the area right there, yeah? Mm-hmm. So I probably chose to go like this and call this area 1 and area 2. Is that what you were asking me?
Yeah, because like I drew it so there's like a smaller rectangle on top.
Yep, you could also go like this. Shouldn't have. So you went like that? Mm-hmm. So you'd have, can I call that area 1? Can I call that area 2? And area 1 is going to be 12 times 80, length times width. Yes?
Oh, okay, never mind. Yeah.
And by the way, area 2 would be 7 is the length, and the width is, careful, 40, not 140, right? Was that your mistake? 60, that's what I said, not 140. I can't even do the math either, apparently. I just had lunch, bear with me. It's been a long day for me. Okay, and again, very similar to number 15. After the farmer had pushed the cart 12 meters, it was moving at a velocity of 2.2. What's its kinetic energy? So that's how much kinetic energy it actually had. A is how much work he put into it. What's the efficiency? Smaller divided by bigger for the energies. Is that all right? Next. Ooh, way down. You can always count on Paige to pick something near the end. Ah. Do you remember I said it was important for you to remind me to give you a hint? Yeah. I sort of like this. I sort of like this. I sort of like this. Sir, what? Let's see if we can predict what the answer is going to be. Okay. They're talking about how far the car is going to travel. What we're really asking is how much energy do you have to get rid of? Okay. Work is change in kinetic plus change in potential. But Megan, a car is moving on a flat surface, so I'm not going to worry about change in potential. They're not talking about a hill or anything here. And in fact, I think it's just going to be the final, because change ending is final minus initial. Actually, it's going to be minus initial. The final is going to be 0, because you're coming to a stop. So really what we have, Paige, is this. A half m v initial squared, and we'll put the negative there, but I'm going to ditch the negative now. I'm going to say it's a scalar, and the negative is telling me we're losing energy. Okay? You've done some algebra. This would be a good using principles of physics question. Supposing I double the speed. How much more energy is there? This is where we talked about why golf clubs and tennis rackets are getting lighter. We talked about how 4 times as much more energy. 4 times as much more energy. You know how much more distance you're going to need to stop, my driving friends, if you're going twice as fast? Not twice as much. You know how much more distance you're going to need to stop? 4 times. And it doesn't matter how good a driver you think you are. That's physics. I'm sensing some personal experience.
I almost got hit by a car today.
Who did?
Gabby.
Gabby.
No.
Almost got hit by or almost hit into? I suspect maybe you have more of an active verb in this story.
So I was driving, and there was a stop sign, and I thought there was another stop sign on like their side.
Uh-huh.
It was a through road. So like I saw a car coming, I was like, oh whatever, it's a stop sign out. Like I got there first, so it's my turn. So I went to go turn. So there was a through road, so that guy kept going straight.
And you cut them off?
And I cut them off, and they braked.
How close did they come?
So it was like that.
So had they been going even a smidge faster, because that smidge faster would have been squared. And see, the reason the distance is 4 times bigger is because you'll notice over on this side page, there is no distance squared or force squared. That relationship is linear. Friction can only apply so big a force. The rest has got to go into the distance. Doubling the velocity gives you 4 times as much kinetic energy. You can't make the force 4 times as big. Your distance is going to be 4 times as big. So you know what? I'm pretty sure the answer is going to be 32. Is the answer B? I hope. I can crunch the numbers and find out. Okay. The other way, by the way, you could have done is, if you didn't want to do this algebraically, Paige, you could have actually solved for the force, because you know the first distance, 16. Sorry? Let me read.
It's 60 times 4.
Ah, duh. No, why is it's C? Now I got to puzzle this out. I'm going to do this the long way. Force times distance equals a half mv squared. We can actually solve for the force. the braking force. The braking force is going to be 0.5 times 1500 times 8 squared divided by the distance, which was 16 meters, Mr. Dewick. I thought the answer was B, 0.5 times 1500 times 8 squared. Oh, you're right. Yeah, twice the speed, 4 times the distance. You're right. 4 times 16 would be 60. I'm just doing my times tables wrong. I doubled the distance instead of 4 timesing the distance. Okay. How many of you have ridden a bike before? Okay. So let's suppose you want to go from 0 to 10 meters per second. Then you want to go from 10 to 20 meters per second. How much more energy does that second one take? It takes way, way more energy because of that squared. This is why in a car, you can't just hold the gas pedal down and keep going faster and 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 faster. Eventually, the amount of kinetic energy your car can put out gets limited. This is also why cars accelerate really fast at low speeds, and they don't accelerate all that fast at high speeds. If you wanted to see how much this took, this would be change in kinetic. It would be a half m. V final would be 10 squared minus a half m 0 squared. Compare that with this one. It would be a half m 20 squared minus a half m 10 squared. In this first one, you get 100 times m divided by 2, 50m. Here, you'll get 400 times m divided by 2. Take away 100 times m divided by 2. You get 300 times m divided by 2. And you'll notice, it takes me 3 times as much energy, even though I'm still doing a 10 meter per second speed increase. This is why when you're going fast on a bike, it's so much more work to go faster. Nothing to do with your shape. Nothing to do with how athletic you are. Physics. It's not a number. It's kind of related to the one that Paige just asked me. But I like that question. Okay. Any others? Next. Keep going. You're all here. You must have had some questions. 34, since we're in the 30s, apparently. Did you get A okay? Oh, okay. By the way, the answer to B is going to be, doesn't matter if the change in height is the same, it's a scalar, so who cares whether the roller coaster or the slide was steeper or shallower? That's the nice thing about energy. A. This is actually a little trickier question. I mean, there is do you see a change in height? Say yes. Do you see a change in speed? Say yes. Is it a yucky curved path? We're clearly going to be using some energies along the way here. So I would start out in my mind saying to myself, I think it's going to be kinetic initial plus potential initial equals kinetic final plus potential final. Does this question mention heat? No, it says friction and air resistance are negligible, so I'm not going to worry about plus heat. Are any of these 0? I think we'll assume we start from rest. And we're going to temporarily pretend, for energy purposes, that the ground is right there. Okay? What we're going to end up with is this. Hey, the mass cancels. They want the vertical height, so Gabby, I would divide by G. And I'd get this. My initial height is going to be my velocity squared, my velocity at the bottom, and then a 2 and a G. Is that okay, Jake? So far, so good. Do I know G? Yeah, what's G? Yeah, I'm not going to use the negative because it's scalar, right? Do I know V at the bottom? No. What else have they told me? Which kind of a distance? I think they've told me the range from unit 1 from a projectile. I think what they've given me is dx. Do you remember horizontally when we were, because once you leave the slide, you are a projectile, briefly. What was the horizontal distance equation for, what was the acceleration horizontally? 0. In fact, you may remember we had this, where, Megan, this one and that one are the same thing. How can I figure out Vx? I think Vx, my horizontal velocity at the bottom of the slide, is going to be, Diana, the distance horizontally that I travel in how long it took. Now, the other thing they could have done is they could have told me how high the bottom of the slide was from the ground and told me how long it took me to get to the... there's all sorts of other options, but anyways, this is nice, this is nice. It's going to be 6 meters divided by 0.45 seconds. How fast was I going at the bottom of the slide? 13.33333 or yeah? So I'll carry a few extra 3s, and then I'll say that's going to go right there. The height's going to be 13.33. I got the number on my calculator. Squared divided by bracket 2 times 9.8. Double check that one to make sure I was good. Zoop. Yep. Okay. If we start from the same vertical height, part B, but it has a much steeper slide angle, who cares? You're still going to end up with the same amount of kinetic energy at the bottom if we're ignoring friction and air resistance. What if we started twice as high? Well, the equation for potential energy is mgh. You didn't hear me say any squares or anything. Twice as high means twice the energy. Doesn't mean twice the speed at the bottom, because you will square root to find the speed, but yeah. Where's the really nasty one? I think there's one really nasty one in here. Oh yeah, this one here, 18. Anybody figure out number 18 on their own? Because I'll be impressed. This goes back to what I was just saying, which was asking, hey, what if you double the height? What happens to your speed at the bottom of the slide? Pardon me?
Yeah, I didn't know that.
So let me do that one. Okay? I mean, Dorothy, I did say it's a curvy path with a slide. I'm seeing a change in height. Yeah, this looks like a job for energy. So I wrote down kinetic energy initial, potential energy initial, kinetic energy final plus potential energy final. I said, it does say we're starting from rest, so I can ignore my initial kinetic. And I said, temporarily, I'm going to let the bottom of the slide be ground 0. So I'm going to say final is 0. And what I wanted to get was an expression for the final speed. And it turns out the final speed at the bottom of the hill is always going to be 2 times g times h square rooted. So I wrote, this is Vf. What if we double h? I said if we double the height, instead of h, I'm going to have a 2h right there. You can get this later, Dorothy, if you want to. Just watch for a bit, because you're missing stuff when I'm writing this down. What if I double the height? I replace, can you see, Dorothy, the h with a 2h? Which really gives me just an extra root 2 kicking around. There's my original 2gh in the square root with an extra root 2. I said, you know what? If I double the height, my speed isn't twice as big. My speed is root 2 as big. Okay? So then I said, okay, they're asking how far sideways it's going to travel. You can see, Dorothy, I called that dx. I said dx is vxt. I said time's going to be constant because we're dropping the same vertical distance. No matter how fast you're traveling sideways, your vertical free fall time is going to be the same. So all I said was, all I really need to worry about is what the heck is happening to this? Because whatever's happening to Vx, that's what's going to change the horizontal distance dx. So I said, well, doubling h increases your velocity at the bottom by a factor of root 2, which would then give you an extra root 2 in this equation, which would make your distance root 2 bigger. Not twice as big, not 4 times as big, root 2 as big. Now, that's doing it algebraically. The other thing you could have done is just make up reasonable numbers. Hey, let h be 5. What would 2h be then? 10?
Yeah, that's right.
And that works too. I'm okay with that because most of you are planning on going to post-secondary next year. You want to get used to the abstract proofs a little bit, so I'm going to push you in that direction. And my nerdish heart loves these. I got a little smile on my face. If I start changing colors and things, that means I've become engrossed in the question, and I'm really getting into this one because it was worth switching colors a few times and doing all sorts of neat stuff. If I use a therefore, then I'm particularly proud. Hey, therefore, I found, yeah. That's probably the toughest question, by the way, in the whole package, is that one there.
Do you like this question?
I think I want you to understand how potential energy, work, and kinetic energy are related. The fact that they're not necessarily one-to-one, you got to think about it because velocity's got a squared in it, right? Don't always just assume twice as high means twice as fast, not necessarily. Don't always assume twice as fast means twice as high, not necessarily. By the way, the other easy way, the really straightforward way to think about this is we said if you double the speed, you have 4 times as much energy. Yes? What's the opposite of if you double the speed squared? You're squaring the factor. What's the opposite of squaring? Square rooting. If you're going from the potential back to the kinetic, it should be a square root function, which it is, because that's kind of going in the opposite direction. Another way to think about it. Just thought of that one now. What can you expect on your written section? Absolutely something like number 13. Okay? And what I mean by that is you can expect 1 or 2 questions with a curvy, yucky path, with a change in height and a change in speed. It may have heat, it may not. Now, how can I tweak this? I can give you a speed at the top, which I did in this case, and say, here's how much heat there was, find the speed at the bottom. Or I could give you a speed at the top, which I did in this case, tell you the speed at the bottom and say how much went into heat. Okay. They all start out the same way. Most common dumb mistake that I see is on this line right here, I'll see kids divide by heat instead of minusing heat to get this by it. So they suddenly forget their math 8. Like, really?
The heat always goes on the final side.
In the way that I've set these up, here's what I'm saying. Here's how much energy you started with. You don't have the right amount of energy at the end. Some of it's missing. Where did it go? Heat. You could put it on the left side, and the author of the workbook that I'm using tended to do that. What he was saying is how much work was done. The amount of work that was done on this object was the change in potential, the change in kinetic, and whatever energy you put into heat. That's how much work you did. So he's using a different he's focusing on the worker. I'm focusing on the workee, if that's a word. Let me look at written questions. So you definitely, somewhere you're going to get a graph, right? It may be a nice little triangle, it may be 2 rectangles, maybe a trapezoid, but we've done one of each. Somewhere I'm giving you a question where I'm going to expect you to clue in that if you know the amount of work done, like in A, you can then figure out the amount of kinetic energy, like in B, and therefore then figure out a speed or a height, like in, because instead of asking you maximum speed, I could have pointed this car straight upwards or pointed my little gun straight upwards and say, how high does it get with no ceiling in the way? Yeah, okay, so 20 here. I gave you the heat, and I said find the speed at the bottom. Did I do that in the other one as well? So again, please be. I would feel also comfortable giving you the speed at the bottom and saying find how much heat. Oh, I like 22. I like 22. Here you go. Here's what I was talking about. So here is where I give you a speed at the bottom. I say how much heat. And then now this one, is there a change in height? Yes. Is there a change in speed?
Yeah.
Yes. Is there a yucky, curvy path? We could, if we were really gluttons for punishment, do this with Unit 2 and Unit 1. We could actually go winner minus loser. We could actually find the acceleration. We could actually find the friction force. We could actually find... Anyways, Part A asked you for the how much energy. What is Part B asking us to find, Megan? Now, you'll notice how they phrased it. Average force of friction. And how many marks is it worth? I don't think they want me to go winner minus loser. I don't think they want me to go mg parallel. I don't think they want me to go mg parallel is mg sine. I don't think they want me to go the normal force is mg perpendicular, which is mg co. I don't think they want me to, because you know why? How many marks is it worth? And especially, what did I find in Part A? So, number 2, I said, how much work is force times distance? Heat. That answer right there is how much work was done by friction. Which force creates heat? Friction. Which distance? The distance along the ramp. Why? Because isn't that which way friction is acting? And you'll notice I wrote in red, oh, that's why they told me how long the ramp was, because I hadn't used that 60 at all. I was kind of going, what was the point of that? Oh, by the way, the fact that you know that the front, that the height is 20 and the hypotenuse is 60, could you find angle theta? Yes. Could you do this with winner minus loser? Yes. Could you figure out the friction force? Oh, did they give you mu? Ah, so that would run you into an impasse. You would suddenly go, I don't know the coefficient of friction. Also, I'm doing way too much work for 2 marks. I think they just want you to clue in that the friction force is going to be the heat divided by the distance of the ramp. Average force of friction is 193. I doubt that's constant. I'm fairly certain, Jake, that that changes, because my experience has been the faster I move my hand on a rough surface, the hotter it is on my fingers. So I think as you're speeding up, the friction force would probably be increasing, and that's probably why they said average force. Right? And if you don't believe me, if you're bored, even on these tables, if you press down with your fingers and go really fast, you can almost go fast enough to burn yourself. Certainly, yow, I can get some heat, and you'll find not much heat going slow, way more heat going fast. I think friction force would change. Megan wants to try. Try it. Push down and go really hard. Yes?
It's a really gross sound, too.
It's a sound, but also there's enough heat there. You're like, you could probably burn yourself if you went a whole length and really long. You guys are lucky. So you guys have all heard my yell to wake you guys up, right? I'm not going to do it right now. It used to, for the first 7 years of my teaching, when I had a blackboard, I didn't use a yell to wake my kids up. I just walked to the board with my fingernails, and I would go back, forth, back, forth. Once I went for 2 minutes straight, nonstop. I timed it 120 seconds, nonstop. Kids were almost crying by the time I was done. But you know what, Mabad? They weren't sleeping. They were awake.
I'll never forget being in Miss Wiles' class, and I had science at 10,
Mhm.
and I was leaving for a lunch tonight, so she put me in your classwork, and I sat right here. And I was so terrified. You were like making them watch something, and you were being really loud, and I was scared of you ever since. Because I had to write a test before I
I thought, and I was in the middle of my test, and you did the yell, and I dropped my calculator, and oh yeah. Memories. Yeah. So I had an impact on you, apparently. No wonder you sat as far away from me as you could when you got here. Hopefully you found my bark is much worse than my bite, but my bark is pretty loud. I had 3 years ago a student who had a hearing problem. I didn't find out till partway through the year because the student hadn't told me. He sat in the back row corner, and I'll call him Billy. Billy, I finally got this little form. It says I'm supposed to put you in the front row so you can hear me better. And he just looked at me. Mr. Dewick. I said, oh, so you don't have a problem hearing me? Mr. Dewick, no problem. I got a good loud teacher voice. That's a gift. Things I've never been told. I can't hear you, Mr. Dewick. Okay, I think I like this question, if I hadn't said so already. Nice little question. Any others? I mean, it's a short unit. There's not as much to it. You need to know, Jake, the 3 definitions of work. Force times distance. I guarantee that's going to be on there. Area under a graph. And the one that's really the most flexible is change in kinetic plus change in potential. In fact, that's really where force times distance kind of comes from. Because if it's change in potential, it's force times the height. There's going to be one efficiency question. Oh, I don't know if it's on. I think maybe on one of my tests. I think on one of my tests, I tell you the efficiency and I ask you to find what the power in is. You still go smaller number over bigger number, and if you know the efficiency, it's just straight cross multiply to get whatever's on top of the other fraction by itself, right? I talked about the storing energy in a spring car graph thing like we've done, and then finding out how fast you're traveling after the trigger or the gun or the spring is pulled. It's a short unit. It's worth 6%, so the first 2 tests were each worth 9%. This will be worth 6%. Momentum is also worth 6%. Generally, because there's less trig, kids find this pretty good. Most common mistake, by far, see where the hand is right there? They write the squares, they forget the squares, because they're so proud, especially for something like, especially for something like this, where you're so proud of writing that wonderfully big equation and canceling out the masses if you can. You're so proud of all the things, and the number of times I've seen like something like this written correctly, and then I see the squares written or not, but it's clear because I typed it into my calculator. They forgot to do it on their calculator. So double check for squareds before you hand it in, anytime there's kinetic energy. Any others from the review?
Did you not go through it and like circle the ones you like on this?
I kind of just have now with you guys.
Enough?
I've told you the written pretty close. There's going to be a couple of roller coaster-y, water slidey-y, down a hill questions. I'll bet you one is going to have friction, in which case I'll probably tell you to find the heat. I'll bet you another one has friction. I'll tell you the heat and say find how fast it's going at the bottom. And probably one won't have friction, and I might say how high did we start, or something like that. The using principles of physics, I gave you a hint. My little rant right here. There's your hint. The idea that people think going twice as fast takes twice as much energy. No, it takes 4 times more energy. Certainly the difference, by the way, if you're in a car accident, the difference between being in an accident at 20 kilometers an hour and at 80 kilometers an hour. 80 kilometers, 80 divided by 20 is 4 squared. You'll be doing 16 times more damage. That's why those high-speed accidents are just so much more fatal. It has nothing to do with how good a driver you are. Oh, and it's going to take you 16 times longer to come to a stop. So those you young, dumb drivers with your licenses, I also say, hey, when it's raining, when it's snowy, slow down. It's typically the guys who are like, well, I'm a good driver. Look, you can't argue with the universe. The physics says it has nothing to do with how good a driver you are. You can't possibly stop in the same distance that you could before. You can't. Figure it out. You're teenagers. You generally have to make your mistakes and learn from them. Hopefully Gabby learned from hers. Yes? Hopefully your parents aren't listening to this particular video.
I think the worst part about that was because I cut him off and I was turning. I drove in front of him like a block. And I was just too embarrassed, so I pulled into the gas station and the path.
So I've been in, we'll pause for a second.